Welcome. In this video we're going to be learning about the equilibrium constant, also known as Kc. Make sure you're familiar with Le Chatelier's principle before we look into this. Okay, so let's say we have a reaction. A plus B makes C and D. The reaction's been balanced for us and they've told us that the forward reaction is exothermic. Now, what would happen to the position of the equilibrium if I decrease the temperature? We know, according to Le Chatelier's principle, it would shift towards the right. As a result, I'll have more products than reactants. How about instead of changing the temperature, we increase the pressure? Again, this would push the equilibrium towards the right because there are more moles of gas on the left, less moles of gas on the right, and as a result, it moves to the side with less moles of gas. Now, saying right in both scenarios is a qualitative way of describing the position of the equilibrium. In both scenarios, they're moving towards the right. However, what if we want to compare them and know which one has gone more to the right? Did decreasing the temperature shift it more to the right, or did increasing pressure shift it more to the right? For this, we need a numerical way of comparing them, and that is where the equilibrium constant comes in. So, the equilibrium constant is going to be a number, and this number will describe the position of the equilibrium. The number will fall anywhere on this scale, greater than 0 up to 1, and greater than 1. If the number is exactly 1, that means the position of the equilibrium is in the middle. So therefore, the concentration of reactants and products at equilibrium are the same. However, if the number is less than 1 but greater than 0, then that means that the position of the equilibrium will be towards the left. So the amount of reactants will be greater than the amount of products. And finally, if it's on this side, greater than 1, that means the position of the equilibrium is towards the right. In other words, the amount of reactants is less than the amount of products. So now we have a numerical way of saying the position of the equilibrium. Instead of just saying left and right, which is not very good for comparison, we can now use numbers to describe the position of the equilibrium. A quick side note, the value for Kc can never be 0 or negative, so always remember that. Okay, so let's say we have our two reactions again, and for both of them we've been given the Kc value. The Kc for the first one is 10, and for the second one it's 2. So can we now compare the position of the equilibrium in the two reactions? Well, first of all, we can see that both numbers are greater than 1. That means in both reactions, the position of equilibrium is towards the right. However, the first reaction has a much larger Kc value than the second one. 10 is greater than 2, and that means the position of the top one is far greater towards the right than the bottom one. So in the top one, the proportion of products is much greater than reactants compared to the bottom one. Okay, so now let's see how we can work out the value for Kc. So here's our reaction. The first thing we're going to do is write the Kc expression, and to do that, we're going to simply put the products above the reactants. So the products go here, and the reactants go at the bottom. So for this reaction, it's going to look something like this. C times D over A times B. The final part is that whatever the balancing number, that becomes a power. For example, in front of A, we have 3. So the power of A becomes 3. And in front of C, we have 2. So the power of C becomes 2. B and D both have a 1 in front of them. So we can just simply leave them as B and D. Also remember that square brackets represents concentration. However, this is the concentration at equilibrium. So make sure you don't accidentally use the starting concentration. Because we're talking about the equilibrium constant, we have to use equilibrium concentrations. Okay, so here's an example question. We're going to calculate the value for Kc and also the units. So this is the reaction that we've been given, and the question says 0.2 moles of phosphorus pentachloride decomposes in a vessel that has a volume of 5 dm cubed, and then the equilibrium mixture contains 0.08 moles of chlorine. Calculate the value for Kc and its units. Now when we do Kc calculations, we make something called an ICE table. I for initial moles, C for change in moles, and E for equilibrium moles. And then finally, once we have equilibrium moles, we can divide it by volume to get us the equilibrium concentration. Okay, so we're going to write down the reaction above, and what helps is to put a squiggly line between the reactants and products. So here we can see that PCl is a reactant and PCl3 and Cl2 are products, so we put a squiggly line between them. Of course, you don't have to do this, but it just helps so that you don't get confused. Now remember, reactants get used up, so their moles will decrease, and products are made, so their moles will increase. The next stage is to look at the question and fill up as much of the table as we can. For example, we know we have 0.2 moles of PCl5, and that is the initial moles. Of course, at the start, products will be 0 because we haven't made any yet. We also know that the equilibrium mixture contains 0.08 moles of chlorine. So on our table, we're going to go to chlorine and equilibrium moles and put 0.08. Okay, now we can work out the change for chlorine. It started at 0, it's gone up to 0.08. So that means the change must be 0.08. Once you've worked out the change for one of them, you can now use the balancing equations to work out the change for the rest of them. So we can see that they all have nothing in front of them. Based on this, I can now say that all of them will have the same changed moles because it's a 1:1:1 ratio. Okay, now the final part is to work out the equilibrium moles of PCl5 and PCl3. Let's start with PCl5. We know it's a reactant, so it's going to get used up. Therefore, the equilibrium moles will be how much you had at the start, take away how much it changed by. And that's going to give us 0.12. Then moving on to PCl3. Again, how much we had at the start was 0. It changed by 0.08, but this time we're going to add because it's a product. And that gives us 0.08. Perfect. We've worked out the equilibrium moles for all three components of the reaction. However, Kc requires equilibrium concentration. That means we have to divide them all by the total volume. The question has told us that the volume of the whole vessel is 5 dm cubed. So we're going to divide all of the moles by the volume, and that's going to give us the concentrations. Okay, so now that we have the equilibrium concentrations, we now can use this to work out our Kc value. So just to recap, we have just worked out the concentrations of PCl5, PCl3, and Cl2 at equilibrium. So our Kc expression is going to look like this. The products are going to be on top, and the reactants are going to be at the bottom. There's going to be no powers involved because the whole reaction is a 1:1:1. Next, we're going to plug in the numbers that we worked out, and then that should give us a value of 0.011. Okay, so we've worked out the value for Kc. We can see that it's less than 1, so that means this reaction will have a position towards the left. The next thing is work out the units. Now we want to work out the units for Kc. Again, we're going to have our reaction. Now remember, the units are going to be based on the units of concentration. We know the concentration units is mole per dm cubed. So we can simply say moles per dm cubed times moles per dm cubed divided by moles per dm cubed. Now we're going to cancel out, and that leaves us with simply 1 mole per dm cubed. And that will be the units for this particular reaction. The units can change depending on the reaction, and sometimes if the top and bottom are the same, they will fully cancel out and you might even have no units. Let's try another question. So here we have a reaction and they've already given us the equilibrium concentrations. That means we don't need to do the ICE table. What is the value for Kc in this reaction? So the first step is to make our Kc expression. Products on top, reactants on bottom, and don't forget the powers. Then we can simply use the information they've given us and plug it into our equation. And that should give us a value of 11.5. So this reaction has a position of equilibrium towards the right. As for units, again, we're going to use moles per dm cubed, and we're going to cancel through, which should leave us with 1 over mole per dm cubed. And we're going to bring the bottom part of the equation up, which means we're going to flip the sign on the number. So mole becomes mole minus 1, and dm minus 3 becomes dm cubed. Okay, next part. Here's another question based on the same reaction. Let's say we've already been given the value for Kc and the concentration of oxygen and sulfur trioxide at equilibrium. However, we want to work out the equilibrium concentration of sulfur dioxide. This is also a common style of question. So all we're going to do is first of all write our expression. Then we're going to again plug in the numbers that we know. This time we actually know the value for Kc, so we can simply plug it into our expression. Of course, we don't know the concentration of SO2, so we'll leave it as it is. Now we're going to try and make SO2 the subject. So we're going to rearrange so that SO2 squared equals the following. Next, we're going to remove the square by square rooting both sides, and that gives us a final answer of 0.219, which is the concentration of SO2 at equilibrium. Hey guys, if that video helped you, support our channel by liking, subscribing, and sharing it with your friends. And more importantly, if you still have questions, drop a post on our forum at ExamQA.com, where I will personally be there to help answer your questions. Mohammed signing out.